All right, welcome everyone. A couple of things before we go to our guest speaker. The information for the REU symposium was sent out. I sent out I sent out a template and I sent out a link that was from the Duke team to submit your abstract. So they wanted me to remind you all to submit that abstract. Once they receive your abstract, they're gonna schedule your speaking time. So they're kind of waiting on that. So if you haven't, who has not submitted their abstract yet? Okay. Everybody. Okay. So submit your abstract. It doesn't have to be fancy or long. Does everyone have the link? Does anyone not have the link?
I may not have the link.
Okay, I'm gonna resend it to everyone today.
Thank you.
Okay. So get that abstract submitted, by tomorrow at the latest. How about that? Okay, I think they had said the 14th, but I want Athena to be early. Okay.
And
Oh, great. Thank you.
yeah, and also as you're submitting that abstract, send it to us as well so we can see. It'll help us with
Yeah.
our blurb and reporting. Haha.
Okay, any other questions about the REU presentations, showcase, etc.? Okay, Sandra, do you have anything before we move ahead?
No, just making sure that everyone is registered. Everyone's supposed to be coming to our in-person showcase. Flights, just hotel booking and all that stuff. We just want to make sure logistics are there. Oh,
Mhm.
Ela.
Hi. So Dr. Limbrick had asked, um, we're working on the same project. So is it okay that we do one poster, or did y'all want an individual poster like for each of us?
That's a good question. I think one poster would be fine in that case. What do you think, Sandra? Yep.
Yeah, I'm fine with one poster and then whatever specific area you're working on, you present during that time. So,
Okay. Thank you.
all right.
Any other questions?
Oh, Donovan, go ahead.
Yes. So, going off what Layla said, so we do have a collaboration poster of it's going to be Layla, Adonis, and Tay. But also we have another poster that I'm in charge of. And they'll also be collaborators on that poster as well. So it's probably going to be two posters submitted from Dr. Limbrick's lab.
Okay, two posters, three people.
Two posters, four people.
Four people. Oh, okay, got it.
All right, thank you. That should be fine.
Yeah. Okay, anything else? All right. All right, shall we move on to our guest speaker? Tingjun or Dr. Chen, are you ready?
Yeah, I'm here.
All right, so welcome. Dr. Chen is a assistant professor at Duke, and I'll let him give his background.
Yeah. I've been around for about 4 years. I graduated my PhD from Columbia University. I think that was back in summer 2020, and then COVID hit the time, so Duke had to delay my start time by a year. So I spent a year at Yale working as a postdoc researcher, um, actually hosted by the other Athena PI, Tingjun. So I was still in New Jersey, but I was able to spend a year working with people from Yale. And then I moved down to Durham summer 21 and then started here at Duke in fall 21. So I'm kind of wrapping up my fourth year here. So I primarily work on all types of networks that bring, data from one place to the other. This could be large scale, fiber optic networks that connect data centers, which are, tens of kilometers all the way up to hundreds or thousands of kilometers away from each other, even across the ocean, across the continents. And also last mile wireless access. That's how every one of us can use our phone, which is, wirelessly connected to cell towers on the street or Wi-Fi access points in the building, which allows us to actually connect ourselves to the rest of the world, right? So I primarily work on, wireless wired networks that, brings connectivity to everybody so that people can work on getting higher bandwidth data for, Zoom conferencing, for watching, YouTube videos, Disney Plus these days, ESPN, and all this kind of stuff. So my work is pretty hands-on and experimental. So pretty much everything we work on here at Duke have a test bed, which allows us to actually evaluate how, the proposed, system architecture or algorithms would actually work in real life scenarios. So, that's why all my students have to actually be in the lab, because they have been, taking measurements every day to validate all kinds of, behaviors, observations that we've been, seeing, collecting from different types of networks, right? So, but before that, I actually came from a information and communication theory background. So I was basically working on communication theory and information theory when I was an undergrad. Basically, all kinds of equations. You only need a piece of paper and a pen. You basically work on proving different types of equations, lemmas, disproving things, proving things. But my PhD study, my graduate school is kind of, transitioning from the more theoretical part of the work to a more hands-on part of work. And then I actually enjoy that process quite a lot. Although things may take longer to be done, it's a pretty pleasant to see, you have some idea that works, on a piece of paper, and then you can run simulations to validate the ideas, and then eventually you can actually build a test bed, a network, to actually turn those ideas and equations into something that you can actually measure by hand. And looking at how does that measurement results correlate to or compare to what theory predicts, or what computer simulations predict. So to me that was pretty satisfying. And then if you were to ask me some of the coolest application that we've seen that can be provided by these networks today. So everybody knows that we're getting data service connectivity from Google, from Amazon every day, and all these data centers have been connected using underground fiber, and many of these fiber optic cables go across the states, across the country, and even across the ocean, right? So if you were to imagine what other functionalities or capabilities these underground fiber cables can do, can any one of you guess, what other things can be realized using fiber optic cables? It could be used for decoration for sure, right? You've probably seen, decorations using fibers and so on, but what is the other application that, these underground undersea fiber cables can do? Anyone have any thoughts? Yeah, can you speak up? Yeah.
Um, when I think of fiber optic cables, I think of like data transmission, or really like the telecommunication networks and stuff.
Yeah, so that's
So
what they're used for, right? Traditionally, over the past decades, people have been using fiber cables to deliver, from the very beginning, few kilobits per second, all the way up to date. You can actually deliver multi-terabits per second data over a single fiber strand, right? But what is more amazing is that, you can actually turn fiber cables into a sensor. If you have undersea fiber, you can use the undersea fiber to detect earthquake, right, from some volcano, from some other continents, which are thousands of kilometers away from, where you are. And then more amazingly, recently people from North European countries, they've been using undersea fibers to keep track of blue whales, because blue whales are emitting, acoustic sounds that people, human ears cannot hear. But those acoustic waves, when they propagate through the water, can actually be picked up by the by the undersea fiber. And then by analyzing those acoustic waves, you can actually track the living habits, the migration pattern of the blue whales in very deep ocean. Yeah.
Oh,
Leila?
I imagine that those fiber optics, they have like bonus sensors. It's kind of a bonus add-on to their primary function.
Yeah, yeah, exactly. Leila, you want to say
Yeah.
something?
Yeah, so you said they can be used as some sort of like sensor, so could people utilize them for like security purposes?
Yeah, yeah, very good point. So there are commercial, fiber optic sensors, right? Basically, like, human voice is actually within a frequency range that can be picked up by the sensors, by the fibers, right? So every floor that we're living in, especially university buildings, we have fibers actually going across the ceilings of our offices and everything, right? So if people have access to the end of the fiber, they can very easily put in an interrogator device and then try to pick up the signal and then reconstruct human conversation from the signal that's being picked up by the fiber, right? So that's why when companies are selling this product, they have to put filters to filter out human voice frequency range. So, people cannot use the interrogators for bad purposes, right? So, but exactly that's, if that's how people are able to actually tap out of conversation. And then recently, people have also shown that if you have, fibers deployed around campus or around the city, you can also use the underground fiber to recover, human walking behaviors above the ground, and even to reconstruct the sound of, let's say, a music playing at the chapel, or thunderstorms in the neighborhood, right? So all the sound effects can actually be translated to some effects which can be picked up by the fiber, and then you can run all kinds of reconstruction algorithms to reconstruct those sound effects, right? Yeah, so these are things that we work on these days, and then it also relates to quantum, because Duke actually has a very strong uh, quantum research center, right? So if you're thinking about how we can embed quantum information, these are basically single photons that carry quantum information. We can also send those photons across kilometer distance fiber, and then we use a detector on the other side of the fiber to detect the state of the photon on which we encode quantum information on. So that's why I started, as you can see, I started with from a very theoretical, classical communication perspective, and over the past, I would say, 15 years, I gradually, go to the other extreme, which is very hands-on, very experimental, and then you start to you keep developing, discovering new interesting ideas as you move down the path, right? So that's kind of my my research journey. And at Duke, I teach different courses at both the undergrad and graduate level. So I teach Internet of Things classes, which together with Sandra's team, we've been working on a series of tutorials which we use together with local public schools and private schools to run these educational and outreach activities, with the goal of letting the students know, you have all these smart devices, right? The cameras, the doorbells, all these things around you can be connected to the internet to become something that you can control, you can use to sense and understand the environment, right? So we're basically building around, the topics of Internet of Things to let students know how can you take, a piece of microcontroller hardware, you are given a set of, sensor peripherals, how do you actually connect the sensors to the microcontrollers, how do you write programs to monitor different properties of the surroundings, and then how do you connect those devices to the cloud, how do you construct database to collect organized data, and how do you, build visualization and data analysis tools to help you understand the data and maybe use the data to predict the trend in the future, right? Let's say if you now can collect, over a week of data about temperature, humidity trend in your environment, is there a way that you can use the data to build a model that helps you predict what's going to be the temperature, humidity in the next day or two, right? Yeah, Leila, please.
Okay, sorry. So when you're talking about predicting, what could happen with fiber optics, would you be able to like connect it to a machine learning model that would then be able to almost take, like you said, take the data that is being collected and then use that to predict what you had said?
Yeah, exactly. That's actually what many people are working on these days, right? Depending on, so typically what we do is, we try to visualize, we try to process and visualize the raw data in different forms, and then try to observe if there's any common obvious features that can be extracted from those results, right? If the features are obvious, then probably we don't need very sophisticated machine learning models to help us understand the data. But if sometimes we cannot see very clear features, or if the data is too noisy, many of the features are probably buried under the noise, then that's where the more powerful machine learning models would come in to help us really understand the relationship between the input data and the outcome in a way that human eyes cannot easily observe. Right? So many of the workloads that we look at today actually relies on machine learning models, but many cases we don't actually have to go for very sophisticated advanced models. Sometimes these processing tasks can be handled by relatively moderately small models these days. Um, yeah. So yeah, I think I briefly touch upon what I do in research and also what I teach at Duke. And then every year, we host high school students from the neighborhood, sometimes even from other states. And then we've also been hosting REU students uh, over the past few years. So I think I can probably stop talking, and then if you guys have any questions, I think it's more important and more interesting if you guys can let me know, what's your thought, and then what are you getting out from these REU experiences, and then any questions about, I don't know, college research, um, choosing majors, I'm happy to answer those questions. Yeah.
I have a quick question. So you mentioned that you came from like an information and like communication theory background, and like over the past 15 years, you've gradually shifted from a theoretical like standpoint to more hands-on. Is there like a major mindset shift that you had to go through when you were making that transition? I know it was more gradual, but is there like a really
Yeah, I think that's a good question because I was we didn't I did my undergrad in China, so we didn't have the structure of REU, but there are similar programs happening there as well. So basically, what we did in our junior year, or even sophomore year, is that we can write to professors and research groups who are interested in working on to ask for the opportunity to participate in a research project for, let's say, a 3 month over the summer, right? So what I did was basically I wrote to, I don't know, 20 professors around the world, and then I went to Columbia, which is actually the lab I did my PhD with later on. So when I joined the lab, basically the students mentoring me, he was a pretty hands-on guy, and then he basically threw this project in front of me and say, let's work on this. And at that time, I have some background on embedded systems programming, with MATLAB, C++, and so on. But I was not very, motivated to work on hardware. But somehow, because of the fact that I was, thrown on this project, I feel like I have to deliver. I have to, basically complete, the tasks that I was assigned to, right? And then I think that was the 3 months time in my junior year, where I really spent a lot of time digging into the hardware embedded systems world. And then I gradually found out it's actually a lot more interesting, not only because I learned new skills, but also because I was able to see something that I was only able to imagine in my head can actually work on real systems and real device and real hardware. Right? I think after that 3 month of training, similar to an REU program, right? Probably some of you work on robotics for the first time during this REU program. You're probably amazed and surprised by how things actually work in reality. And then that's kind of how I got motivated to spend more time digging into the system, experimental part of the research, right? And then after I went back to my college, after that experience, I chose to do a senior project design, which is actually more on the experimental side. And then I joined the same group for my PhD study. And then, things go naturally. I become more and more hands-on. I start to play with, very different hardware platforms, and then to enable different types of applications. But I feel like that summer, period in my junior year was kind of the transition point that, that made me, attracted me, I would say, to explore this other direction, which I wasn't able to explore before. Yeah, that's why I was happy. I was actually glad you asked, because that was actually very similar to an REU program in terms of the structure, in terms of what you guys were exposed to and have been working on over, let's say, a 10, 12 weeks period. Yep. Ali?
Yeah. So I'm kind of curious to like know the specifics on like photons going through fiber optic cables, because I have like a physics background and I did research on like simulating quantumly entangled triphotons. So do you know how like specifically has it been done yet, or is this like just theory?
It's been done a lot, right? So Duke, we're very good at trapped ion technologies, right? So basically, you put ions in a radio frequency trap. You can apply voltage along different axes of that trap, so that you can actually trap those ions within, let's say, a linear confined space, right? And then if you were to actually make the ions to emit photons, right? So basically, you can excite a laser with very well crafted laser pulses, and then those lasers would hit those ions, and then the ions would lose photon. And then the way you are shining lasers on those ions would actually make the photons to be carrying specific properties, which is entangled or correlated to the state of the ion, right? So that's why, when the photon leaves the ion, the state of the photon would be correlated or entangled to the state of the ion to some degree, right? So one way you can choose to encode information or quantum information on that ion, sorry, that photon leaving the ion, is to choose to design the control pulse sequence in a way that the quantum information would be encoded into the polarization state of the photon that leaves the ion, right? And then if you were to actually connect that, ion trap with a fiber tip, let's say over a very short distance, free space connection, then the fiber tip would actually would actually be able to receive and receive the photons emitted by the ion, and then the photons would just be naturally propagating along the fiber. And then the photon, as it propagates through the fiber, it will experience all the power attenuation, power loss, polarization shift, all the regular behaviors that any photon, any particles would experience as they propagate through the fiber, right? So what we need to do is that we have to prepare the quantum state by understanding the, let's say, polarization encoded onto that photon. And then let's say after the photon is propagated along, let's say 5 km or 10 km fiber, we can take another detector and measurement device at the end of the fiber and try to measure the polarization state of the photon after the photon propagate across the 10 km fiber, right? And then if that measurement tells us the polarization state of the photon is what we expected, then we know we establish a remote entanglement between the ion and the photon across this 10 km fiber link, right? So that's what we call an ion photon remote entanglement, because of the way that we can program or excite the ion to release a photon whose polarization state is entangled with the ion. And then we have to make sure that the polarization state of the photon persists across the propagation over the fiber, right? So that's actually what we are doing here at Duke. We're actually building up the infrastructure. So we're actually connecting buildings and labs over field deployed fiber. So hopefully we'll be able to actually send the photons across 2 buildings across the campus in the next, I hope in the next month or two. So that's exactly what we are working on these. But the challenge is that the Duke technology relies on measuring and counting every single photon that arrives at the photodetector, right? So that completely depends on the emission rate, efficiency of the trap, right? So it might only be able to emit 20% of the photons, and then maybe another 10% would get lost during that transmission over long distance fiber because of power attenuation and so on. So at the end of the fiber, we are only probably collecting 1%, 5% of the photons that were emitted from the ion. That's why a lot of these quantum experiments, you have to repeat the same measurements over and over again, so that you can collect maybe 1,000 photons over the course of maybe an hour or so. So you have some statistical confidence to talk about the correlation, the entanglement rate between the ion and photon, right? So these are pretty technical skills. If you guys are interested in, we are happy to actually show the lab. I think maybe sometime in the future, if there's a plan, for a series of lab tours and things like that. Yeah, Emily.
Hi, thanks for coming in to speak with us today. I was just kind of wondering, from being like a PhD student to a postdoc to a professor now, how has your day-to-day or like what you do for work changed with those roles?
It changed a lot. I would say, as a PhD, I mean, first of all, right, from undergrad to PhD, that was already a huge change because we are not assigned with homeworks, coding assignments every week. We don't have a deadline to submit our homework assignment. The deadline became, you have to get a good understanding of the field. You have to finish literature review. You have to design your experiments. You have to collect the data. You have to analyze data. You have to write the paper. So the entire research development journey as a PhD student is already very different from an undergrad. So we've seen a lot of undergrads coming to a PhD program with the same mindset as an undergrad. They're waiting for us to, assign them weekly homework. But what we actually want to see is that students in the PhD program should be a lot more motivated to actually find out, what's happening in the field, what is the leading technology, which are the leading groups in the field, and then we can, try to push forward the boundary of the technology, right? So I think, just changing that mindset from, waiting for assignment, looking at lecture notes to very proactively looking for research papers, searching for literature, and then understanding the most advanced technologies and development in the field. I think that mindset was something that we're hoping that PhD students can develop in the first year or two, because that kind of lays the foundation of your research in the remaining of your PhD program, right? I would say that's the biggest difference from from undergraduate study to PhD study. And then another thing is PhD study is not only about developing technical skills and background. There's also a lot related to soft skills. How do you actually advertise your work, as you guys are doing like all the poster sessions and everything? How do you convince readers and audience that what you are working on is valid, is interesting, and useful for the field, right? There's a lot of marketing as well. You have to know the work very solid. You also have to know how to best present and deliver the work in front of audience who may have different backgrounds coming from different fields, right? That's why I would say it's probably like 70% technical and 30% actually all the soft skills. You have to know how to write good code. You need to know how to collect good measurements. You need to know how to write good papers, colorful presentations, good delivery, and all these are other things that you'll be able to develop over the course of a PhD journey. And then going from PhD to postdoc, I would say it's more as training the mindset in a way that you are working with your PI more as a colleague rather than as a student, right? So sometimes we ask postdoc to help us supervise undergrads, master and PhD students. Sometimes we write grant proposals together. Sometimes we would ask postdoc to help us review papers and help provide suggestions and comments to papers, presentations from other group members. I think postdocs would take a lot more responsibility in actually helping the PI in understanding and mentoring the students' work and tasks. And then actually going from postdoc to an actual faculty, to me, it's like it's basically three jobs at the same time, right? You have to be a PhD yourself because you're always learning new things. And second, you're also working as a postdoc for yourself because you have to mentor the students, you have to mentor your postdoc as well. And then as a faculty, you not only have to worry about getting funding, funding new research directions, but also you have to be responsible for teaching undergraduate and graduate courses every year, right? So it's basically research, teaching, education, these three tasks that we care about every day. So I'd say it's very different. I mean, but over time, although you get a lot more things to do, I think over the time you kind of get used to that momentum. You know which things to prioritize. You know how to allocate time for different workloads and so on. I think, I would say it's a pretty smooth transition. It's like, you spend your first year in grad school, try to go from an undergrad mindset to a graduate student's mindset. I spent my first year as a faculty to go from, the mindset of a postdoc to the mindset of faculty. And then with, good colleagues and support from around, you get used to, you get pretty quickly adapted to the environment, right? So that's what I've been learning over the past few years from the other colleagues as well. Yeah. Hi, Leila.
Hi. Is there anything you would recommend for like an undergrad to do to start preparing themselves kind of like early for a PhD program so that you can kind of not bypass the transition from undergrad to, a PhD program, but just kind of get like a head start on it, if that makes sense?
Yeah, so I think especially for STEM field, right? For let's say ECE, computer science related fields, I would say one thing that we look a lot for is very good and organized coding experience and background, right? So if you can link your resume to your GitHub page, you can, post in the public a few projects that you are the most proud of, that you have written solid, high quality code for. Many of us actually, including myself, I actually like to look at students' GitHub profile because by scanning through the code, right, you get a very good sense of the way students think about the problem as they code the problem in different languages, right? So put comments in the code, try to beautify, optimize, organize the structure of the code in a way that as a first-time reader, I can very easily understand your thinking, your thoughts as you construct the code and the program, right? So for me, that's actually a lot more valuable information compared to looking at the website, looking at all the other profiles, because code is something that has to work, right? If you if you write code, you'd better write code that actually works before you put them online. And then just by looking at the way the code was written, right? Let's say you do things, using 3 to 4, for loops, compared to you do the same thing but using a highly efficient data structure and get rid of all the for loops, right? Just by observing, these minor differences, as a faculty, we can very quickly tell if the student is a good engineer, a very good coder, a solid programmer to begin with, right? Because I do believe in the engineering field, what I'm telling my students these days is that if you're entering a PhD program, let's be a good programmer first, right? I don't mind my students spend the first 2 years, 3 years just to get themselves trained to be a solid programmer. Because eventually, if you go find a software engineering job after graduation or research scientist, you will likely be writing code every day, and then you cannot get around with all the coding related problems in your interviews in the future, right? So I think and also nowadays a lot of the work that we do relies on writing hardware and software code with very good performance and highly optimized, right? So that's why for the work that I do, I always suggest my students to it's okay to spend the first year, the first 2 years, try to learn how to write good code, because we're providing you the opportunity to learn how to code in grad school. Otherwise, you would have to spend other time to work on to get prepared for all interviews and internship opportunities and so on. So I think you have to prepare your resume, your transcript, maybe your other portfolios. But one thing I would like to say is a GitHub page with a few open source project that you are the most proud of, with very clean, organized structure of the code. I think that's what a lot of faculty members would actually look for, right? So we see resumes with very similar format, but we look at GitHub code with very different structures. That's kind of where students may stand out from the pool. Yeah.
I don't really like take up all the time, just one more question. So I'm an electrical engineering major, and I just finished my second year. And so right now we haven't had that many like coding classes. I've really learned like the most about coding while being here at A&T in the REU program.
Yeah.
And so I guess my next question is, are there any like programs or maybe like certifications that you could think of that like I could do on my own that would be able to help me learn more like when I go back to Hampton?
Yeah, I think definitely, right? There you can look up, Coursera, right? MIT has this open course. Like all these are good resources that you can look at the lecture videos, and then many of them actually come with, you know, written assignments and also coding assignments. You can, can finish those, and then I think even on, what you guys are working on as part of the REU, right? If there is a coding component, if there is a, measurement experimental component, feel free to ask your PI, right? If the paper will be published, if it's okay for me to include these as my portfolio used for, college application or grad school application, right? I think, most of us would say yes, because, we'd like to see the things to be used by other people as well. Yeah. Hi, Hasti, did I pronounce that right?
Yes, you pronounced it correctly. When you were talking about like kind of like the colleague relationship with your PI, and I know this varies case by case, different PIs have like different management styles, but for your case specifically, how was that relationship? Like how hands-on was your PI? And then how did that dictate the kind of deadlines you set for yourself moving forward within your program?
Yeah, I think that really depends on the group, and then probably also the seniority of the PI. So when I was a student, right? So my advisor was hands-on at the very beginning, but then, as he became more and more senior, and had been taking on different roles from the department, from the school, people become less available for research discussions, right? That's very natural uh, in universities. So, which is good for me because I like to work on things by myself, right? I don't like to be thrown on an idea and then work on the deliverables, right? That's why, the fact that my advisor was becoming more and more hands-on actually provided me the flexibility to work on and look for new research directions and opportunities by myself, which I liked. And after I started here at Duke, which I believe it's the true for most, assistant professors right before their promotion and tenure process, people want to get results out as quickly as we can, right? So that's why most assistant professors would be pretty hands-on. And then we have a lot of ideas in our mind. That's why, our students are very busy, implementing our ideas and try to prove, if our ideas are good or bad, if it works or do not work. I think for all assistant professors, I think you can imagine that um, it's going to be a lot of work, right, for the student because, there has to be deliverables, there has to be the timelines. I don't think that's a challenge because that really depends on, for students who'd like to work by themselves, I gave them the flexibility to think about, what they want to work on. For students who needed to begin with an idea or to need to begin with, some more, better defined or more clearly defined pathways, I gave them some directions so they don't get lost when they started, right? So that's why eventually I think this is really a case by case thing. For some students, I let them work on the things that they're capable, they're interested in working on, if they know exactly what's going to be the path moving forward, right? For other students, then who may need more guidance, then we will do our best to provide them the guidance. That's what most assistant professors would do. I guess when you grow more senior, then these really you see larger variance, right? So there are people who are still very hands-on, like writing code, doing measurements in their 50s, right? But a lot of people also transition to more of a management role and leverage postdocs and other more senior group members to manage the newer generations. So I think it varies a lot for groups with more senior people, but for like I would say younger groups, I would say it's pretty uniform across the country. Like we all want to get the things out quickly done as quickly as we can. Yeah. Yeah. Adonis or Peyton, how do you?
Hey, how you doing?
Good. Yeah.
Well, my question was, how do you see the future of wireless networks and IoTs? evolve in the next 5 to 10 years, especially since AI is coming up and it's a big thing.
Yeah. So that's why that's actually what we are working on and thinking about every day, right? I think that the challenges are, you know, we want to connect more and more devices around the world, which would require larger bandwidth to actually carry the data, to move the data from one place to the other. And then once you start to run AI models on these devices, whether it's on your cell phone or on your base stations, then these AI models would consume compute power, which turns into real energy power, right, from the power grid, from the battery. So that's why a lot of our work on how to actually optimize or co-optimize the hardware and the AI models in a way that the AI models runs the most energy efficiently on that particular hardware platform, right? So we don't want to run, general purpose large AI models everywhere. We want to customize, tailor different models so that, for this particular task running on this particular device, we would get the most energy efficiency and the most benefits from these combinations of hardware platforms and AI models, right? So one thing I'd like to say is telecommunication networks have been developed a lot in the past, 50 years, right? And then many signal processing techniques we use today, including how those technologies are implemented on highly optimized, silicon integrated circuits. I don't think those things can be easily replaced by AI very quickly, because AI is good at solving problems that do not have a very clear, mathematical structure or relationship between the input and output, right? So for many of the communication tasks, we know this is the input sequence of data. We know this is the channel that connects the input and output. We know how to estimate the channel very well using conventional classical signal processing techniques. In those scenarios, we actually don't like to use AI because we know how to do that the most efficiently using conventional algorithms and conventional silicon and integrated circuit technologies, right? So whenever people tell me or ask me, what's your view on adding AI capabilities to future wireless computer networks, I always say, if this is a task that people know how to do very well, efficiently, already at very low power, then we don't even need to bother the use of AI, right? So today, the cell phone, when you are decoding data bits sent by, nearby base stations, which might be carrying, Zoom information or carrying some other video traffic, right? So the hardware knows how to decode the bit sequence and how to recover from these lossy transmissions very well. But these are technologies that have been developed before the existence of ChatGPT and the large models, and have been improved by hardware companies like Qualcomm, Ericsson a lot over the past years, right? So I don't see a very quick pathway that AI models can replace these conventional signal processing blocks in the very near future, because this is what every film has adopted and has been using for the past, decade, right? And of course, once this becomes a reality, then, companies like Qualcomm, they would be the first to demonstrate that there will be some benefit or some gains in actually adopting these AI technologies, right? So maybe AI is good for analyzing the data to provide you some other capabilities, but just in terms of encoding, decoding the information bits and recovering, recovering from lossy, corrupted packet transmission, these are things that we actually don't rely on AI to do these days, right? So that's something that we have to be careful when we design future networks and think about if they should have a component based on AI or not. Yeah, yeah. Tao, or how do I pronounce your name?
Oh,
Sorry.
you're good. It's Tay.
Okay, yeah,
Yep.
please.
I'm not sure if you're able to speak on this, but I'm a part of another research program at UNCG where we're learning about military defense technologies. And so I was wondering if you possibly could like guess or like basically like guess like what type of methods they would use in terms of incorporating machine learning or things like AI in order to, or like I heard you talk about the fiber optics and how they're able to interact with signals, of how they are able to incorporate it like within their ability to like protect the country pretty much.
Yeah. So that's definitely relevant, right? So a lot of the work that military does is, for example, right, if you want to detect unknown signals or unknown objects which might be entering your territory, right? So you can use traditional radar or imaging-based techniques. You can also develop machine learning techniques which allows you to understand something that you probably haven't seen before, right? I think signal processing in that context is good at understanding something that you know some properties about, right? For random stuff, let's say, somebody sends a signal that nobody else knows the pattern, the frequency of that signal, then that's where machine learning can come in and at least tell you at the very beginning if this is a signal that you have seen before or not, right? So machine learning is very good at finding the pattern, the relationship between data that the model has seen before versus the data that the model hasn't seen before, right? So in those cases, we can typically rely on machine learning models to understand, if the received signal type is something that is legitimate or illegitimate, and then we can go from there. And then machine learning has a much broader application in vision-based applications, right? Because for radio signals, we're dealing with electromagnetic waves, right? You have to digitize the radio waves. You have to do a lot of signal processing. But for all the vision-based techniques, if you were to detect, hidden objects or something, then the input is basically an image with different resolution, right? And the images are, more static. You know exactly these are the RGB channels. There's a range of the color pixels of every channel. So machine learning models are very good at understanding, these properties when it's given a particular structure, right? So that's why, for those vision-based techniques, people would be relying more on machine learning to understand the behaviors of different types of images collected by different sensors. But for sure, there's a lot of applications there that will even like all the autonomy. How do you actually learn the environment? If you have, multi-model sensors that capture different properties of the environment, how do you, fuse information, knowledge from different sensors, right? That provides different types of outputs so that, the vehicles, the robots can better understand the environment, right? So that's where machine learning comes in to help you understand, how things work together. Yeah.
Other questions?
Yeah, Ali.
So going back to what Hosty mentioned earlier about like your path towards being a PhD, would you have done anything differently? Would you have majored in ECE now that you know that that was the path you wanted to take, or would you have still stayed in the same major?
Yeah, that was yeah, so when I applied for college, um I was choosing between electrical engineering and architecture, right? Um and the reason I didn't go to a architecture major was my college entry exam score was not high enough. The architecture program was actually more difficult, actually the most difficult to get in at the time of my college application, right? So electrical engineer was my second choice because my testing score was not high enough. I couldn't select, or go for the architecture major. But otherwise, I would probably be doing something very differently um, these days. And then if I look back in time, I'm not saying that architecture is not a good major. I still have a lot of interest and passion in architecture. But if you look at the current industry and what people are going after, right? I feel like electrical engineering, computer science, it's probably the right choice for me. Uh, if I were to go back, 15 years when I applied to college. Um, I just feel like, I cannot comment on how, or I cannot imagine how my life would be if I were to go to architecture these days, right? But I can only say that, I chose electrical engineering and then I've been enjoying that major very much. Uh, I think what's the most fascinating part, what's the most fascinating is that there's always something big that comes out every 3 years, every 5 years, that would surprise the whole world, right? And then that gives us the opportunity to look for new research directions. And also as a faculty, I think what's equally interesting to me is we get to work with students coming from different generations, right? So I work with students who were born in the 90s. Now I work with students who are born after 2000. I see a very different mindset across the generations, and then I see different passions, right? They become more and more passionate about technologies, and also with the better technologies, they can probably you know uh, make their learning curves easier over the next decade, right? So that's why I think this is a very unique and exciting field, at least for the next, I would say, half century. Probably, if we don't run out of power and energy uh, around the around the world, I would say, it's a very exciting area. Um, I wouldn't regret anything. I think one thing that I would regret was I feel like, I would have spent a lot more time learning about coding, how to write better code when I was an undergrad, because I feel like I spent a lot of time in grad school to pick up the coding skills because I wasn't very, formally trained to write, very good Python code or C++ code or Java code. I was kind of learning everything by myself. And a lot of the things I did later on was kind of learning from scratch. Um, if there were like a series of, tutorials and courses, then I would, sit down and actually use those resources to improve my coding skills if I go back. I think that would have saved a lot of time for me um, when I was doing my PhD. And then my second advice was that try to try to take notes of everything, right? This could be notes of the measurements that you did today. This could be the notes on the person you met during the event this week. Uh, Sometimes I look past, I was trying to remember, I met this interesting student, I met this interesting person at that symposium a month ago. Something is related, but I could not remember the name of the person or where the person came from, right? So that's why now I started a Google Doc uh, file. I keep track of all the people I talked to at different venues. This could be conferences, this could be workshops, this could be outreach education activities. So every time, just in case I suddenly remember something important in the future, I always have a reference to go back to and remind me this was the person that I spoke with uh, maybe a year ago, maybe 2 years ago, right? I feel like it's probably also because I don't have a memory as good as I had 10 years ago. I start forgetting things, but also I feel like that was a very good exercise to keep because you don't know if something or some person would become relevant again in the future, right? So if you keep that log over time, if I now look back the note I start taking 4 or 5 years ago, you will be surprised and amazed by how many people you have met from very different groups with from very different backgrounds. And then this list of people eventually will become your pool of resources when you are looking for internships, looking for jobs, looking for collaborations, looking for other opportunities, right? So I'd say, taking good notes about your experiments, about your research, and also taking good notes about your uh, study life, right? People you've met, faculty, teachers you've met, and then your colleagues, peers. You may lose connection after graduation, but you might be reconnecting to each other after 10 years, 20 years, right? So just having that list of people, you would be, I mean, it might be, shorter list to begin with, but over a course of, 5 years, 10 years, you will be surprised by how big of a network you will be able to grow over that longer period of time, right? So that would be, my other suggestion, how to learn how to write good code and to take, good notes on your experiments, your work logs, and also the people you've met. Yeah, that's what I will say.
Thank you.
Excellent advice.
I think it was actually because I start forgetting things. I mean, 10 years ago, I can remember people I met, 5 years ago,
And it gets worse.
and it gets worse. And that's why, when I was getting closer to finishing my PhD, I started this document that I try to keep track of people I met at conferences and
It's a
students
great
I
idea.
spoken with.
In the olden days, they called it a Rolodex, where
Oh,
they
yeah.
have contacts, and
Yeah,
every
yeah,
time you met someone, you'd fill out a little card. That's, before.
yeah.
Way,
I think people
before that.
before they would take like a small notebook with them, right? But nowadays people are using their phones.
And then we had business cards and all that.
Yeah, yeah.
Tingjun, I have a question. Did you always know you wanted to go into research and teaching, or was there a time that you thought you would go into industry?
I think at the very beginning, in the first half part of my PhD, I wasn't sure which direction I would go. I guess it was really, when I started my, I think, fourth year in my PhD, I started to realize this is something that I'd like to, continue working on. And then I see more and more passion working in this direction compared to, I guess, going to industry and then work on, what your mentor, a director tells you to do. Uh, and also, I think it was because I liked interacting with the students. That's another thing that you won't be able to get from industry. Uh, I think that was really, after you've done good research, you've collected, feedbacks and, positive feedbacks and good impacts from the community. I think that's when I decided to give it a try to apply for, faculty positions. Yeah.
Any other questions?
This is a question I usually ask. So, in the midst of everything that you do, what's your work life or optimization looks like?
I would say, to be honest, right, to be straightforward, as an assistant professor in a good university, it's like, if you don't have kids, it's like 90% work, 10% life. To be honest, that's to be fair. But it's only a period of time, and also it's a period of time in your life that you would be the most passionate about the work you do, and you actually have the energy and bandwidth to do it. Right? So I feel like, after 5 years, even if I want to work on the same thing, I may not have the energy and time to keep up with the pace that I'm able to work on things at this moment. So I feel like it's a good period of time for me to put 100% of my energy on something that I'm passionate about. And then, who knows what's going to happen after 5 years, right? So that's why maybe I'll have kids, maybe I'll be busy with other stuff, maybe I'll start a company. But this is the period of time that, for assistant professors on tenure track, there's a very clear goal, which is to get tenure, right? And then we spend 20% of our efforts to get to that point. And then that means you may lose a bit of life, which is, I mean, to some people, to some people, it might be a disaster, a nightmare. But for me, it's actually okay because, I know I want to get to a certain point within this amount of time, right? And then I'll probably be relaxing more after reaching that point. And then I think, things will get balanced out. You don't have to be, you don't have, it doesn't have to be balanced every single day, but, over the longer period of time, if you take a lot more work in the current 5 years, you can probably be more relaxed in the next 5 years. So I would say, to be very honest, it's a lot of work. It's a 24/7, I mean, not 24/7, but probably 14/7, uh, 14/7 work. I think 100 hours every week, that's pretty normal for us. But that's what we are paid for, right? For research, for education. But after you reach to that, milestone, you know, I think I may find something else to do. I mean, could be new research directions, could be a new venture, right? Who knows what's gonna happen?
There's got to be one thing you do to relax, Dr. Chen.
I run. I
You
run
run?
with my wife. Yeah, she runs a lot faster than I do, but I try to catch up with her. I run. I swim. I do some sports. Um, during that 10% of my time.
Okay.
And then I have two cats at home, right? So I play with my cats every day during after work. So yeah, I would say it's still a lot of work to be done every day, but I don't regret. I think this is for me, this is the right time to do the right thing. So I don't mind spending 100% of my time and energy on this. Yeah, at
Good,
least
but I'm
now.
glad you're running.
Yeah.
and swimming.
Yeah, that's
I
right.
don't want to scare them. It's like, okay, research is not it. It's all that. I
No,
was like,
yes, I
no,
think
you have something else you do other than being in the lab and teaching
yeah, yeah, for sure. And cook, I mean, have to
and
eat.
cook. Yeah, you got to eat.
Gotta eat every day. Yeah.
Oh, good.
Okay, we're out of time. Thank you so much, Tingjun.
All right, thanks everyone. Yeah, let us know if you will be around on campus. I think many of you are probably not on site. Just let us know if you're be here, and then we're happy to show you around the campus and the labs and everything.
Don't hang
Thank
up
you.
yet. Hold on.